So let's try answering this question, and with this we'll be able to end vector triple product. Answering this question will help us develop an understanding about how to find the direction along which a vector might lie, because this is one of the most complicated ones. Sometimes you're more likely to encounter simple cases. So if you understand this case, then simple cases are even more easy to deal with as to where the end product lies, right? What if I ask you this question? What if I ask you, where does your A cross B dot C cross D lie? What will you say? So the question is, where does this lie? The answer is, it's a scalar. So if it's a scalar and not a vector at all, then talking about where it lies is actually absurd, because this thing is not a vector at all. This is a vector, this is a vector, right? This A cross B is a vector, C cross D is a vector. When I take their dot product, I finally get a scalar. So scalar lies on a number line. It doesn't have a direction, right? So there's no point talking about it. So remember, A cross B cross C cross D. Now this is a vector because this part is a vector, this part is a vector. The cross product of these two vectors is actually going to give me another vector. I need to see where that vector lies, right? So for that, what we will do is, we will slightly rearrange this. So what I can do is, I can write A cross B cross C cross D as something like A cross B dot D into C minus, can you tell me the next part? Yes, A cross B dot C into D bar. So it's very simple. I've treated this as one vector. I've taken the dot product of the farther vector from this and then multiplied that with C bar. Then I've taken the dot product with C bar, right, this part, multiply that with D finally. So just the normal expansion of your cross product and nothing else, nothing more special. So if you look at this, this is basically your box ABD into C bar minus box ABC into D bar. What is box ABD? A scalar, right? Some scalar, some number. Box ABC also is some scalar. Some scalar into C bar, some scalar into D bar, right? And then you're taking the difference. That means this vector lies in the plane of C bar and D bar, right? That's obviously true, because you're taking some vector lambda, you're taking some scalar lambda, multiplying that with C bar, then you're taking some scalar mu, multiplying that with D bar. Now this vector is obviously along the plane containing C and D, right? Because your C is here, lambda C will be something like this, and your D is here, lambda D will be something like this, mu D will be something like this. Then you're adding this lambda C and your mu D. So you're adding these two vectors, so make a parallelogram having these two as the edges, and this will basically be the result. And this result is obviously in this parallelogram, so in the same plane as both these vectors, right? So that's what the expression is, the understanding is. So this vector lies in the plane of both C and D, right? Now let's try rearranging this a little bit more. So what I will do is, I will reverse the order of this. So what I'll do is, I'll write minus C cross D cross A cross B. Can I do it? Yes, I can, because this is a vector, let that be some P bar. This is a vector, let it be some Q bar. So P bar is the cross product of A and B, Q bar is the cross product of C and D, right? So if you're taking the cross product of P and Q, I can also reverse the order. But what I have to do, I have to add a negative sign, right? So this is the same as this, because though I have reversed the order, I have still accounted for that by using this by this negative sign, right? So it is the same thing, but you will actually see why I have done this. So what I will now do is, now I will use this as my vector. So let this be some vector, R bar. So this is like the R bar cross A bar cross B bar. So again, I'll use the vector triple product formula. So the minus sign will remain as it is, but C cross D will be dotted with the vector which is far from C cross D, and that's your B bar. this part, this is into A bar, because you're taking the dot product of this and the farther thing, you have to multiply that to this vector. And then what will be the next thing? You'll take the dot product of this part with this, and then you'll multiply that with B bar, right? So this is C cross D dot A into B bar. Now multiply this negative sign inside. So finally what you will get is box C D A into B bar minus box C D B into A bar, right? This is a scalar into B bar, this is a scalar into A bar. That means this vector, this same vector is also lying in the plane of A bar and B bar, right? Because again this is some scalar into B bar minus some scalar into A bar form, right? So just like this case is also very similar, and the vector is the same, right? Just that I've reversed the order using this negative sign, but this vector and this vector are the same vectors, right? So this vector that you see here lies in the plane of A and B, and also it lies in the plane of C and D. That means it lies in the common region of the plane containing AB and CD. It lies in the common region of plane containing A bar, B bar and C bar, D bar. Remember, and they are getting this result because your A and B are together and your C and D are together here. So it lies in the common region containing, of the plane containing AB and of the plane containing CD, right? So remember the order, remember this understanding, the way we actually evaluated this. So you might have a plane containing A and B like this, and you might have a plane containing C and D like this, So this part which intersects this part that you see here, so this plane is infinitely long, right? Both these planes are infinitely long. So what is the place of intersection or the region of intersection? Basically this straight line here, because two planes will intersect along a line. So your vector A cross B, C cross D might lie along this line, right? So what you have to understand is it lies in the common region of the common section of the plane containing CD and the plane containing AB, right? So with this we complete the entire topic called vector triple product. Let's move on to the last small subtopic of this huge chapter called vectors, and that's basically reciprocal system of vectors.